Attention all visitors, attention all visitors. The Intrepid Sea, Air, and Space Museum will be having its blast-off launching space shuttles presentation starting right now. And my name is Samantha. I am an educator here, and
I'm Yoshi. I'm also an educator here.
and she's going to start us off.
Okay, so welcome to the Intrepid Air and Space Museum. The Intrepid is a non-profit educational institution. Our mission here at the Intrepid is to increase your awareness and understanding of science, history, and service. And the way that we do all of that good stuff is through exhibitions, programming, and demonstrations just like this one. We also want to honor heroes, educate the public, and inspire youth. Okay, with that being said, let's jump into blast off. So, if you look right behind you, at the wonderful Space Shuttle Enterprise, I'm sure you've all had a moment to sort of walk around it and take a look. By a show of hands, how many of you think that the Space Shuttle Enterprise went into space? Okay, who knows for a fact that it didn't go into space? There we go, loud and proud, right? So the Intrepid, the Space Shuttle Enterprise didn't actually go into space. It was just a prototype. So you can, in this video, you can see the Space Shuttle Enterprise in the back of the 747. Yeah, which is what Samantha has right there. The Enterprise did not go into space. The highest it went was about 26,000 feet, and it travels at about 470 miles per hour. Now, if you know anything about shuttles and rockets, that's not very high, and that's not very far at all, right? So how did we make that jump from not actually going into space to actually getting there? Getting super high up and going super fast. So we launched space shuttles that travel about 17,500 miles per hour. Now that's fast. And not only that, they actually went up to altitudes of about 350 miles. So we went from traveling nearly thousands of feet to miles. Alright, so that's a very big jump. So how did we actually get there? Well, the answer to this is, well, a little bit of physics and a whole lot of fuel. And that's what we're going to get into in our demonstration here today. Now, the first thing we're going to be talking about is the physics. And Samantha's going to talk you through Newton's 3 laws of motion and how they apply to launching space shuttles into space.
Okay, so in order to do some physics, we need some physicists. So any volunteers, preferably smaller physicists. Yeah, you want to be a physicist? You can do it. I won't bite. I had lunch. All right, you can actually come up over here. Any other small physicists? Don't worry. Physicist is scarier than it sounds. Are you come on? Come on, come on. All right, we're actually going to be launching some rockets. So if you want to launch some rockets, come up. All right, what's your name? Joseph, and you want to come up? What's your name? Erica? All right, so we have our 2 physicists here, and we're going to start out with the first law. Right there it says inertia. You can come up closer to over here looking at these 2 rockets. Over here we have 2 straw rockets on our launch pad. Right? Now, inertia. First question, kind of hard. Are these things moving? What do you think? Are they moving? Yes or no? Are they moving? Right now, are the straws moving? Right now. Are they? I mean,
Survey says
they might be moving because, you know, Earth is moving. Really, really deep philosophical stuff. Everything's moving. But right now, to us, it's not moving.
relative to the Earth.
Relative to the Earth, it's not moving. I mean, relative to everything else, it's moving. So he was kind of right. He's actually a really good physicist. All right, so they're not moving. And inertia states that an object in motion likes to stay in motion. Like when you have a bunch of coffee, you just want to drink more coffee, right? And an object at rest likes to stay at rest. When you wake up in the morning and you're in bed and you're resting, or if you're on a couch, you do not want to get up. Unless you put a lot of force in it. For us, it's either more coffee or an alarm clock. Right?
Or a big dog jumps on you.
Or a big dog jumping on you, right? So, force, it says here, force is mass times acceleration. In order to have a force, we need to move stuff. So all you need to move this stuff is to pull this back and let go. So, yeah. So if you can help him hold it off, yeah. So, first of all, what are the 2 differences between these 2? Right, pull it back. Let's help him out. Yeah, let's pull it back together. Right, so we're gonna pull back, and 1, 2, 3, blast off. Well, yours didn't go. Try switching them. All right, let's try switching them now. So what are the differences between these 2 straws besides the color? What else? What do you see on top? The audience can help out too. What is
Mass. Wait, mass.
Why? What? Yeah, it has less goo, and this goo is clay. But this goo represents your mass. So in order to move more stuff, you're going to need more force. And speaking about force, every action has equal and opposite reaction. So what's happening is that, you can do it again, go ahead. Air is rushing into the tube. Try it one more time. Hold on to it. Right. So air is rushing into the tube and then rushing back out, pushing it against the ground. And that is what is causing our rocket to go up. Because if the air is moving down, which way is the rocket going to go?
Up.
Up. All right. So let's have a round of applause for our young physicists. All right. You guys can go back. All right. We're going to ask for more volunteers later. All right. Want to go this way? All right. So, 3 laws. Okay, we covered that. And we're going to see what's next. So what's next?
Okay, so we briefly looked at mass and how mass can greatly affect things, right? And the thing is, when we're launching things into space, are we launching little lumps of clay?
No.
No, we are launching gigantic things that are super duper heavy. So in this image, you can actually see the space shuttle in launch position, right? It's not going anywhere yet. And if you look at this image, it looks like there's not much going on, but these things are actually really, really big and they're super, super heavy. So the actual space shuttle, which is going to be this little piece right here, I'm going to show you this model. Yeah, please do. So I'm going to show you this model. So the space shuttle, which is going to be this guy right here, is about 150,000 pounds. That sounds like a lot, but let's talk about the solid rocket boosters, which are on both ends right here. Now, each of these guys are about 1.3 million pounds. And this big guy here in the middle, the liquid fuel tank, is going to be about 1.6 million pounds. What about the astronauts and the cargo and the things that they're taking with them? Well, that's really just 28,000 pounds. When we add all of that stuff together, we're actually taking a lot of mass with us, and a lot of it is actually just fuel. So when we go into space, we have to learn how to balance those two things. Mass that we want to get up there, and fuel that we need to take that mass up there. What I mean by that is, as we want to take more mass, we need more fuel. As we add more fuel, we have more mass. And then as we add more mass, we need more fuel, right? Yeah?
And that's why the shuttle external tank is orange now. In the early days of the shuttle, they used to paint them white, and all that white paint on the external tank would add an extra couple tons to the shuttle.
Well, you see, fun fact that I did not know. Woo, fun fact. All right, and now something else to keep in mind is that as you're going up into space, you're actually burning fuel as you get higher. So as you go higher and higher and higher, you're actually getting lighter and lighter and lighter and lighter. All right? So how do they make that perfect balance? So when you look at a space shuttle launching into space, there seems to be a lot of action going on, right? There's cloudy stuff, there's smoky stuff, there's fire, there's amazement. It's like, whoa, all this cool stuff's happening. So today in this demonstration, we're actually going to take a closer look. And we're going to look at how they actually put these things together. So Samantha again is going to come back and talk about how to light a candle, or essentially how we get the space shuttles into space using things like fuel ignition.
All right, so first thing you need, next, you need a fuel. So the fuel here is either aluminum, kind of like burns like a racer, or what is that other thing again? What is it?
The fuel tank.
Liquid fuel tank, right, which is liquid
Oxygen.
hydrogen. Liquid hydrogen?
And liquid oxygen.
Right, this tank here. So, we're going to move on. So, like you said, oxidant. You need an oxidant. Oxygen's great, we breathe it. We also need to burn. You need ignition. You need something to start the fire. And then you have your fire. Pretty simple version of the shuttle. Alright, so here's what we have. This fire coming out of this shuttle using basically the same method like a candle would use.
So I'm going to talk a little bit more about the flames that you actually see coming out of this. So for this, I'm actually going to dim the light back down. Okay, so now you can see there are actually two different kinds of flames. So you're going to see this blue-looking flame, and that's coming from our liquid fuel, the space shuttle main engines. And then you're going to actually see this bright yellow slash orangish color, which is coming from a solid rocket boosters, which remember were on either side of the space shuttle in launch position. Now the differences between these flames. Now someone else in the audience had actually mentioned it before. This liquid fuel tank, what it's actually burning is liquid hydrogen and liquid oxygen. Now do you guys know a molecule that you encounter every single day that's made up of hydrogen and oxygen?
Water.
Water, exactly, right? And that explains why you have this beautiful blue color, right? You're burning a lot of liquid hydrogen and oxygen, and as a result, you're actually creating water. And what this does is actually makes about 3,000 pounds of water every single second, and it generates about 375,000 pounds of thrust. Now that sounds like a lot of thrust, but it's actually nothing compared to our solid rocket boosters. Now the solid rocket boosters are where the main push comes from. The solid rocket boosters actually burn aluminum, and that's why you see this bright yellowish flame. And it's sort of like the same process that you see with fireworks, right? When you see fireworks in bright, beautiful colors, metals and salts go through the same process that aluminum is going through, right, in this case. And that's why you see this one. And this gives you about 2.65 million pounds of thrust. Now that's a lot compared to the 375,000 pounds of thrust that you get from the main liquid fuel tank. Okay, so again, let's come back to this idea of mass with our fuel. I said before that as you get higher up, you're actually burning fuel, you're getting lighter. But guess what? At about 2 minutes into flight, we actually lose our solid rocket boosters. And they get sent back here on Earth, and we reuse them. Now, does anybody have any idea about why we would want those solid rocket boosters to just fall off if they're empty?
Less drag, less mass.
Yeah, what were you going to say?
Then the rocket ship will weigh lighter and you'll get fuel.
Exactly, right? It's going to be lighter. So let's see it in action. Now, Samantha's going to do it again. She's going to show what happens.
Okay, so we are scientists, and you just came up with a hypothesis. What was your hypothesis?
That if you lose, like if that thing falls off, that means you're making the rocket ship lighter.
Right, so if you lose mass, the rocket ship gets lighter, which means it will go faster. Let's see. So, we are scientists, so are we just going to believe a hypothesis?
No.
Oh, we want proof, right? So we're going to ask someone help prove your idea, okay? So I need a volunteer. Do you want to come? Do you both want to come up? Yeah, all right. You both can come up. You are our new physicist teams. NASA has hired you. Can we get some more lights here?
And
All
it makes
right.
it more aerodynamic,
What are your
too.
names?
To what?
More aerodynamic.
Yeah.
All right, so here we go. We're gonna have these two here. You can step up. Here is our new and improved launch pad. A lot bigger than the one before. Here's our rocket. The middle is the shuttle, and the two are the boosters. So we're gonna put it up here. And the way you launch this rocket is by gently pulling this all the way up and then letting it go. Who wants to do the first launch? You want to do it? All right. So you can just gently pull it up. And then let's have a countdown. 3,
2,
2,
1,
blast off.
ignition.
Oh, you have to.
All right. So just drop it instead of pushing it down. All right. Let's try that again. All right, Houston. Let's go. 3, 2, 1. All right. That went pretty high. Pretty high. Maybe you went like slightly almost to the atmosphere. Let's try one more time with only 2. You ready? All right. Let's make sure the plate is on there properly. Okay. 1 sec. All right. 3, 2, 1. Blast off. Not bad, right? Not bad. Okay. Who wants to see it with just 1?
Ooh.
All right. Let's see. Here you go. All right. You can do it together. Okay. So can both of you put your hands on there? Okay. 3, 2, 1. Blast off. Well, that was
1,
pretty
2,
good.
3. He's out.
Awesome. So let's have a round of applause for our volunteers. So this is what this is showing. A couple of minutes into the flight, you lose your fuel tanks. All right, you guys can have a seat now. And you want to take it away from here?
So we lose our solid rocket boosters at about 2 minutes into flight. They drop off already, but eventually at 8 minutes into flight, you're actually also going to lose the main fuel tank, which is the big orange thing that was basically right here. All right. Now, unlike the solid rocket boosters, the main liquid fuel tank is not reused. What we mean by that is that as it's falling down and heading its way back to Earth, it actually gets burned up in the atmosphere. So we can't really reuse it. And if you look at the back, you can actually see the solid rocket booster still falling. All right? So right now, we're actually going very, very fast. And remember before I said that space shuttles, when they wanted to go in orbit, they can go at about 17,500 miles per hour. Now, right now, we're very, very close, but we're not all the way there. All right? And that's where these guys are going to come in. Now, the orbital maneuvering system is going to give the space shuttle the extra push that it needs to get to that 17,500 miles per hour. And this system, along with the reaction control system, uses a very different type of fuel than what we talked about before. We talked about liquid hydrogen, liquid oxygen, and aluminum. But now we're going to talk about something else, which is hypergolic fuel. And hypergolic fuel is actually not very, very good for you because you're toxic. You're polluted. We don't want to breathe these guys in. But they do something very special because when we combine them, they combust. We don't need any of the ignition source that we would need with something else. We don't need to supply it with a spark. As soon as they come together, boom. Alright? So the fuel that we use are monomethylhydrazine and dinitrogen tetroxide. Okay? You guys think you can say that? Monomethylhydrazine, dinitrogen tetroxide? Yeah? No? Okay. So it's really, really tough. Basically, when you combine these guys, this is what you get. You combine them, you get nitrogen, carbon dioxide, and water. And what is that going to look like? It's going to look a bit something like this. Alright? This is what happens when you combine these two guys. You get basically a lot of energy. So where do we use this? Well, I said before that we use it in our orbital maneuvering system, but we also use it in our reaction control system, which you can see on our shuttle. And if you look right behind you, you can actually see that last picture, which is this guy, right over there. Alright? So you can basically take a walk around the Enterprise after we're done with this talk, and you can look for these things. Now, when the space shuttle comes in for a landing, it uses all of these systems. What does it use it for? Well, it actually uses it to flip the shuttle upside down and make it travel back like this. Alright? Now this is how the space shuttle comes in. And then they use these systems again to switch it back over like this. And basically, as the space shuttle proved in 1977, it can come in for a glide landing, sort of like an airplane. And at that point, it doesn't need any of the fuels anymore. It can just glide on down and land. All right, and that's what makes these systems so special. Now, why do we actually care about these, how we get space shuttles into space?